Hello, this is the Mr. Dan Maths channel. Today we're going to be looking at matrices, which are a very important topic in the pure further maths syllabus. Some of you may already be familiar with what a matrix is, but we're going to be properly defining things today, and we're going to be looking at how to do operations with matrices, plus some extra questions which we could do with these very important mathematical ideas. So a matrix is, well, contrary to what some of you might think, is a very simple thing. It's essentially just a rectangular array of numbers. So I could choose what this rectangle size is. Maybe it's 2 rows and 3 columns, and I can fill this up with numbers, okay, of my choosing. Maybe I'll choose, just for simplicity's sake, I'm going to choose 2, 1, 3, 4, 1, 2. So that right there, okay, that is a matrix. Right, so pretty simple. You just choose the number of rows, then choose the number of columns, and you fill the numbers in. Okay? And this is a surprisingly vast and very rich area of mathematics. So you can explore this in your own time, but it is very interesting. Here, what you have to consider are the dimensions of a matrix. As I said, the rows and the columns, okay? And they determine what you can do with those matrices and other matrices as well. Clearly, this has dimensions 2 times 3. I say the rows before the columns, okay? And typically for any sort of matrix, you can say that it's going to be n times m, or it's going to have n times m dimensions, okay? N here is the number of rows, and n is the number of columns. So clearly n equals 2 over here, and m equals 3. Now there's arithmetic that you can do with matrices. So we're going to look at addition of matrices, subtraction of matrices, multiplication, which is going to be a large part of how we're going to do these things, and you could say division as well. I'll just put a star there because it isn't exactly division, it's more multiplying with the inverse, which is division, just not in this. Very strictly, it's not division in this scenario. So let's look at addition first of all, and I'm going to choose 2 simple matrices. All right, I'm going to choose A, which is going to be 1, 2, 3, 1, and I'm going to choose B, which is going to be 2, 1, 4, 7. Okay, if you're going to define your matrices, okay, as A, B, T, or any letter that you want, you have to underline, okay, unless you can write bold, which will be very messy. You should use an underline. So what you have to check first of all is there enough elements in these 2 matrices that I can add them together, okay? And by that I mean, are there any numbers that are going to be left over with no pair to add them together with? Which ultimately means that these 2 matrices cannot be added together. Just eyeballing it, we can see that every number has a pair, okay? There's 4 numbers here, 4 numbers here. So we can actually add these matrices because there's enough numbers to work with over here. But let's say in this matrix I had 6 numbers. Clearly then I can't add these 2 together because I'm going to have 2 numbers left over which are not going to have a pair. They can't be added to something else in the other matrix. Therefore, if a matrix has 6 numbers and another matrix has 4 numbers, or I should be referring to elements because they're not necessarily numbers. So if a matrix has 6 elements and another matrix has 4 elements, I can't add them together because there's not enough elements to add together. I have to pair them up. Now, with addition, okay, it's one of the simpler operations. What you have to do is you just have to look at the element in the other matrix which corresponds to the element in the first matrix. So if I write them side by side, it kind of becomes obvious what I'm doing once I start with the calculations. What you do is you just add 1 to 2. So basically, if I give these labels, so this is row 1, row 2, column 1, column 2, I'm just going to be looking at my final matrix, which is going to be A plus B, which is also going to be 2 by 2. It isn't suddenly going to gain a row, is it? It's just going to be R1, C1. So the first row, first column in the first matrix, A, R1, C1 in the second matrix, which is going to be B. So clearly the first element, okay, which is row 1, column 1 in the matrix A, is going to be 1. In B, the same element is going to be 2. And I'm going to add them together because that's what my operator is. Now, I'm going to repeat this. So it's for row 1, column 2, I'm going to look at row 1, column 2 in the matrix B. This is just going to be 2 plus 1. Same thing here, row 2, column 1, row 2, column 1, 3 plus 4. I'm just going to write down the numbers now. So row 2, column 2 plus row 2, column 2 in the second matrix, 1 plus 7, 8. Crucially, what you can see over here is that the matrix B plus the matrix A is just going to be the same as A plus B, i.e. the order does not matter, okay? This operation is commutative. If you look at subtraction on the other hand, okay, so A minus B, what you'll have is 1, 2, 3, 1 minus 2, 1, 4, 7. Okay, and you do the same thing. So 1 minus 2 minus 1, 2 minus 1, 1, 3 minus 4 minus 1, 1 minus 7 minus 6. Okay, pretty simple stuff. But there is an interesting point to be made over here, and it kind of reveals a deeper structure with matrices, alright? And it's the surprising compatibility with algebra that it's got. If we look at B minus A, okay, we can do 2, 1, 4, 7 minus 1, 2, 3, 1, right here. This will equal 1 minus 1, 1, 6. This matrix over here looks very similar to this matrix over here. It's just the minus signs and the positive signs, they're all swapped around. What you can do is, okay, and this is a very nice quality of matrices, you can actually factor out the greatest common divisor of all of the elements in the matrix. And the greatest common divisor over here, which is most convenient to us, is minus 1. So 1 minus 1, 1, 6 is what I'm left inside if I divide everything by minus 1. This matrix over here is the exact same as the matrix over here, okay? And just as with any algebra problem, what you can do is you can just substitute in your answer over here. Consequently, we can conclude that minus 1 times B minus A is equal to minus B minus A in brackets. Oh, sorry, A minus B is equal to minus B minus A in brackets. Seems like a very trivial fact, but this is this kind of proves that we can use algebra for matrices, provided you know a few extra rules that we're going to cover in multiplication, which we're going to do now. What you've done with addition and subtraction, unfortunately, we cannot apply to multiplication. You can't just look at each row and each column and then just add or just multiply, sorry, and then get your final answer. It's a little bit more complicated than that, and it's kind of like the mistake that people make when they're expanding double brackets. So let's say you have 3x plus 5 times 2x minus 7. Clearly it's just not going to be like this, is it? So there's going to be extra terms which you'll have to multiply like this. So just should remember this from GCSE, like FOIL method. So it's a little bit similar to that. You have to consider other things as well. So let's take these two matrices that we just had. Okay, the first thing you have to consider, in fact, is whether you can actually multiply them together or not. And it's not as simple as just looking at the number of dimensions, because you can actually multiply different dimension matrices together. So 1, 2, 3, 1 times 2, 1, 4, 7 is equal to A times B. It's kind of like 21. 2, 1, 4, 7. What you have to consider is this is a 2 times 2 matrix and this is a 2 times 2 matrix. You have to look at the number of columns in the first matrix that you're going to multiply and the number of rows in the second matrix that you're multiplying, okay? And if the number of columns in matrix A, the first matrix, is equal to the number of rows in the second matrix, then you can multiply them together, okay? To find out the dimensions of the new matrix of my answer, I can just remove these dimensions and the final will just be 2, which is on the outside, and another 2, which is on the right hand side. So the final matrix or the resulting matrix of A times B will be a 2 by 2. Now the question arises, how are we going to multiply these two matrices? And it's easier to sort of visually look at it, and if you do see the pattern, then just practice this until you can kind of multiply these away. And it's certainly more complicated than just adding and subtracting, and not a good quality, just a quality of matrices is that as a result of this process that we follow, A times B will not be the same as B times A, provided one thing is not true, but we're going to go into that. The way you multiply these matrices is that you consider the first row of my first matrix, which is going to be A, and I'm going to consider the first column of my first matrix, okay? And I'm going to look at the elements. So it's going to be the first element of my row and the second element of my row, all right? Then here it's going to be the first element of my column and the second element of my column. I'm going to multiply the first element of my row with the first element of my column to get the first thing I'm going to add together with the 2 times 4 over here, which is going to be my second element in my row, second element in my column, to get my first element in my resulting matrix. No, I've waffled on there for a bit, but I think it's a little bit easier to show you what's happening. Okay, so 1 times 2 is what I'm going to do, and I'm going to add that onto 2 times 4. Okay, and the thing to remember over here is that, let's say that's 2 times minus 4, then you have to consider the minus as well. So you're multiplying the numbers together and you're adding them together in this fashion. So 1 times 2 and 2 times 4. Those are the numbers that you're adding together. So if you evaluate this, it's just 2 plus 8, which is equal to 10. So that's what your matrix should look like for your, that's what your element should look like for your matrix. So 1 times 2 plus 2 times 4. So it's kind of like this. You don't have to consider like with algebraic expansion, stuff like this. So you don't have to consider any like further connections, you just have to look at the corresponding element in the row versus the column. So if I write out my matrix again, it's gotten a little bit messy. write it a little bit bigger this time as well. So 1, 2, 3, 1 times 2, 1, 4, 7. A different colour now. What I have to do is I have to look at my first row and I have to look at my first column, and the first element, the second element, the first element and the second element, I multiply the first element in my row with the first element in my column, the second element in my row with the second element in my column, and then I add those two numbers together. So ultimately it is a pretty simple process, but it's very, very tedious at times. So ultimately what you have to be is very careful. You cannot mess the addition, subtraction, any sort of arithmetic up, because the final answer that you'll get could be way off, okay? The sort of arithmetic we're doing here kind of compounds over, and ultimately you get an answer that is definitely not the answer. But you won't know because there's no way to eyeball. Unless, of course, you're a genius. Then I kind of rinse and repeat the process. So I have column 2 over here, and I have row 1 over here, and I have row 1 over here, and column 2 over here, okay? To get the second element, so row 1, column 2, I'll look at row 1, column 2, and I'll multiply everything together. So if I erase my markings over here, annotations, I'm just going to re-add what the annotations will be over here. So clearly we're still looking at these numbers over here, 1 and 2, but for column 2 now, it's going to be the first element in column 2, which is 1, the second element in column 2, which is going to be 7. First element row 1, first element column 2, multiplied together, and then add with the second element multiplied by the second element in row 1 and column 2 respectively. Just rinse and repeat this process until it kind of gets ingrained in your head, and ultimately what you can do is you can automatically just multiply matrices together. You don't have to do arithmetic on the side. So it will be 1 times 1 plus 2 times 7. So it's just 1 plus 14, which is equal to 50. So that's what my first row, second column looks like. Now, I've got my second row to look at as well, because now I have to work out every element in the second row. So to look at the first column of the second row, I'll look at second row over here, and the first column over here. So you can kind of see it's a very, very monotonous task, very tedious. So it's 3 times 2 plus 4 times 1 over here. It becomes 6 plus 4, which is going to be 10. And repeat again, row 2, column 2, 3 times 1 plus 1 times 7 is going to be 10. The nice thing you can see with this matrix is that everything has a greatest common divisor, namely 5. If I write out the matrix again over here, the good thing is that you can actually factor a 5 out. So you can actually say there's 5 lots of matrix 2, 3, 2, 2. So you can kind of treat matrices as brackets as well. So that over there is my answer for multiplying these two matrices together. If you have the chance of simplifying matrices, I think it's good practice that you do so even in your exam, because it builds a habit of refining your answers, and I think that's very crucial for moving forward with your sort of examination process and learning. Let's go back to my algebra point. Okay, so clearly with matrices you can rearrange all that stuff. You can kind of algebraically manipulate them. is what I'm trying to get at. But it's not the same as just working with variables and multiplying them and adding them, because the rules are different. Crucially, what the main difference is if I have A times B, for which I've done the calculations of here, that does not equal B times A. Because obviously you can see with the amount of calculations I was doing the arithmetic, the rows and the columns kind of switch if you switch the order. So what happens is the answer at the end becomes different. So kind of illustrating this, it's going to be 1 or 2 1 2 1 4 7 times by 1 2 3 1. So if I do the number of rows and columns as different colors, I think it'll be a little bit easy to illustrate. So I'll use blue for rows and green for columns. So this is the number of rows for my second matrix. So I'm going to call this rows over here as well. And the columns are going to be like this. So rows before columns, I have to consider, I'll say this is row A and row B, sorry. Row B, row A, and column B, column A. If I have row B times by CB, and I multiply those together, multiply the matrices, I'll get CA, the number of columns over here, row A, the number of rows in matrix A. I'll be looking at the columns of the matrix B and the rows of the matrix A. If I swap those around, what will happen is, I'm going to illustrate this. What will happen is I'll be looking at instead of CB, I'll look at CA. And instead of RA, I'll look at RB. So the kind of algorithm that we're following, it involves different dimensions than the previous one. That's why with our multiplication, what the thought process that we followed and applied, that is also going to be different. Ultimately, the final elements are going to be different as well, because the addition that you do, the final result that you get for the element, it's going to be different because of the order of multiplications that you had and the different numbers that you used. There is one exception. It's kind of like multiplying everything by 1. And it's called the identity matrix, okay? And it kind of stems from the fact that a matrix will always equal itself, okay? It's just, it's kind of something you have to assume to be true, or something cannot be not itself. So, is there something that I can find that if I multiply it by, pre-multiply or post-multiply, okay? Because the order, again, matters, right? Then it will equal itself. And that matrix over here, if you want to find it for yourself, then pause the video now, okay? Will be this. And I'm writing this for any n-dimensional matrix. So that's what it'll look like. The key idea is that there's a diagonal of lines going down, and everywhere else it's zeros. or diagonal of 1's going down, and there's zeros everywhere else. Crucially, if you multiply this identity matrix with any other matrix, okay, it will equal the matrix that you started with, A. So it's a very cool sort of fact that you can use. Other than that, A times B does not equal B times A. Unless B equals the identity matrix, of course, then A times I obviously will be the same as I times A, because pre-multiplying, post-multiplying doesn't matter when you're essentially just multiplying by A in kind of like matrix speak. Okay. The main fact that you need to know about with matrices is transformations. Okay, and we're going to look at the transformations and the questions that are going to come up with how to use matrices with transformations and how to calculate the matrices involved with transformations in the next video. For now, the basics of matrices are covered, and I encourage you to just work with some basic questions and essentially just look for certain algebraic concepts and try and work with them. We'll look at some additional stuff in the next video as well, such as the determinant of a 3x3 matrix, which will be useful much later on with 3D vectors. Alright, that's it. Thank you.